Hello everyone, welcome to DIYguru. So today, as part of the basic electrical engineering, we have a session on the Kirchhoff laws. Let's begin. So the Kirchhoff laws, basically we have two types. One is voltage law and another one is current law. So we call it as the KVL, Kirchhoff voltage law. One more is KCL, which is Kirchhoff's current law. So before going into the in detail about this, first we'll see why we need to go for the Kirchhoff laws. So why the Kirchhoff has made these two laws. So this is because in the complicated circuits, so when if it is a simple circuit, like if you have a very less number of components, then easily we can analyze the circuit. But when we go for the some complex circuits where many components are there, then it is difficult to find the voltage and currents in the components. Okay, so here the Kirchhoff's laws gives us the flexibility to find the voltage and current in the circuit simple. Okay, so even though the circuit has many components, we can easily find the voltage across the any element and the current through the any element by using this Kirchhoff laws. And also we can easily find the equivalent resistance of the complex networks. So these Kirchhoff's laws are applicable for both AC and DC circuits. So we can solve any circuit by using the Kirchhoff laws. Now we'll see one by one what is KVL and what is KCL. So before moving into the detail about the KVL and KCL, to understand this KVL and KCL, we need to have some definitions. Here we call it as the circuit definitions, like what is branch, what is node, what is loop, network, circuit. These terms are frequently we use while solving the problems for the KVL and KCL. Okay, so here first we'll go with branch. So branch is nothing but it is an element which has the two terminals. Okay, a single element in a circuit is called as the branch. Here you can see in the circuit, like here we have one, two, three resistors are there, and one we have the source. So how many branches are there here? So R1 is the one branch, R2 is one more branch, R3 is one more branch, and the supply voltage is one branch. So a single element in a circuit is called as the branch. Okay, now next coming to the node. So node is nothing but it is a point of connection of two or more elements. So now we know the elements. So this is the element, let us consider. When the point of intersection of two or more elements is called as the node. So you can see here, this is the node 1 node where R1, R2 are connected to this point, and this is also a node. See, these two nodes are same. This is, we can consider it as a single node because there is no other element between these two. So we can consider it as a single node. So where R1, R2, R3 are connected to a common point. And even you can see here R2, R3 and this source are connected to one more common point here. There are no other elements are there in between these points. So we call it as a single node. Clear? And this is also one node because here the voltage source and R1 are connected to the common point. So this is we call node. So in this circuit we have three nodes. This is one node, this is another node, this is the another node where two or more elements are connected together. So that we call it as the node. Coming to loop. So here loop is nothing but a closed path. Here if you see in this circuit we have two loops. So this is one loop because if you consider these three elements, this forms a closed loop, right? You can observe this one clearly. This is closed loop. There is no like open path you can observe. And this is also one more loop. This makes the another loop with the two elements only. R2 and R3 makes a loop. So loop is nothing but a closed path. You can simply remember. Okay. The network. The network is nothing but it is an interconnection of elements or devices. So in these circuits we call it as the elements only. Okay, so network is nothing but the interconnection of elements, whether it is a closed or open circuited or closed circuited, the interconnection of the elements we call it as the network. So network may be an open circuit or it may be a closed circuit. Remember that point. Okay, so next coming to the circuit. So circuit is a same the interconnection of elements which forms a closed path. There should be a closed path, then only we call it as the circuit. Okay, see the difference between network and circuit. In network is also interconnection of the elements, but it can be open circuited or closed circuit. We call it as the network, whereas the circuit is nothing but it is also interconnection of the elements which forms the closed path. There should be a closed path, then only we call it as the circuit. Now I think you are clear about the circuit, network, branch, node and loop. So now we'll go for the KVL and KCL. So first we'll go with the Kirchhoff's current law. So KCL. So the KCL states that here at a node. So KCL is applied at a node. Remember, KCL we apply at a node. Already we know what is meant by node. So all the incoming currents to that node is equal to outgoing currents, or you can say all the entering currents is equal to all the leaving currents. In the another way you can define it as the algebraic sum of the currents at the junction is nothing but node here will be 0. Algebraic sum of the currents at the junction or at a node will be 0, or all the incoming currents are equal to outgoing currents. Here in this figure you can see this is a node. So here we have 5 currents are there. So I1, I5, I4, these 3 currents are entering into the node, whereas I2 and I3 are leaving the current, right? Leaving the node. So simply we can write it as I1 plus I5 plus I4 is equal to I2 plus I3. Or else we can write the same equation as algebraic sum. That is nothing but all the entering currents like I1 plus I4 plus I5 minus I2 minus I3 equal to 0. So both are same only. Okay. So here the same circuit which is representing. So here all the currents are entering into the node, right? So I1 plus I2 plus I3 is equal to, there are no outgoing currents, so simply you can write it as 0. I think everyone is clear about the KCL, the definition or statement. All the entering currents at a node is equal to the leaving currents at the node. So the KCL is we derived from the law of conservation of electric charge. Okay, so it depends on the conservation of electric charge. So the charge entering should be like positively charged particle should be equal to the negatively charged, right? The same way here the entering currents at the node is equal to the outgoing currents at the node. Next, coming to the voltage law. So the voltage law is we apply in a closed path. Remember, to apply the KVL we should have a closed path. So the definition states that the algebraic sum of voltage drops in a closed path is equal to 0. So the algebraic sum of the voltage drops. See, this is the source, we have V1, and here one resistor we have, and another resistor here you can see this one. So the voltage drop across this resistor is V2 and the voltage drop across this resistor is V3. So here voltage drop is nothing but the current into resistor will give you the drop across the resistor. So already we have studied that the resistor will dissipate the energy, right, in the form of loss, or you can say temperature, heat. So here the algebraic sum of the voltage drops, that is nothing but V1 minus V2, V1 plus V2 plus V3 is equal to 0. Here one more resistor we have V4. So algebraic sum of all the voltage drops equal to 0. Or you can define the same statement as the algebraic sum of EMF applied, or the voltage. EMF is nothing but here voltage. You can don't confuse here. The EMF is nothing but voltage. So the applied voltage is equal to the algebraic sum of the drops in the elements. The supply is nothing but this complete voltage should be like appears across, drop across these three elements. So V1 is equal to V2 plus V3 plus V4. That is simple. The source or the applied voltage is equal to drop across the all elements. Okay. So here we need to remember that one point, that so while applying the KVL, the direction of the current plays a very important role. So first we need to determine the direction of the current. We need to allot it current direction. In this direction only we need to apply the KVL. So the same, this KVL is the we derived from the law of conservation of energy. The same, like we know already the law of conservation of energy, right? The energy neither can be created nor can be destroyed. It will be transformed from one form to another form. The same way here, this voltage is fed to these resistors. The same like law of conservation of energy. Here this energy is dissipated in this resistors. So and it will be transformed in the form of either heat or some loss, you can say. So here we'll take an example, some like small example. How will you write this? See here. So this is a simple circuit which has the three resistors and one source. The source voltage is 45 volts. The resistor values are here given. And let us consider the current is I. Now simply apply the KVL. So we know that already the supply voltage is equal to drop across the each resistor, right? So drop is nothing but current flowing through the element into resistor across resistance of that resistor. So simply the 45 is equal to, so what is the current here? I into 5. You can see here. So R1 into I plus R2 into I plus R3 into I. So these all are the drops. The sum of all these drops is equal to supply voltage, or you can tell it as source. So simply substitute the resistor values. So this is the simple KVL equation. You just simplify this equation so that you can easily get the current in the circuit. So one equation we have only one unknown. So simply you just add all these currents, add all these drops and find the current value. Now I think you are clear, right? Kirchhoff's voltage law, just we apply in a loop, closed path. So supply voltage is equal to drop across all, sum of the drop across all the elements. Now we'll take one small example to understand this KVL and KCL. So here we have taken one simple simple circuit. You can see here the circuit, so which has two loops and two sources and three resistors. Okay, so here if you want to apply the KVL, first we need to make the current directions. So I have taken the current direction as this, like this. Now just apply the KVL in the first loop. So drop is equal to the supply is equal to the sum of these two drops, right? So in order to find the sum of these two drops, first we need to find current through the element. So here we know that the current I1 is flowing in this direction, but when it comes to this element here, for this element the two currents are flowing, like I1 is coming in this direction, means from top to bottom, where I2 is coming in this direction, means from bottom to top. So these two currents are flowing in this direction. Then the resultant current becomes I1 minus I2 when you are considering this loop, because this current is dominating when you are applying the loop, first loop. So we'll write the current flowing through this resistance is I1 minus I2. Now you can simply apply 10 is equal to the resistance of this element is 20 into what is the current flowing through this one, I1, plus what is the resistance of this one, 10 into what is the current flowing through this element, I1 minus I2. So this will give you simply the KVL of the loop 1. Now you apply the same loop, same like KVL in this loop. So in this loop 2 will give you this direction. So this is the direct current direction we have applied. So you just take the KVL also in the same direction. So the leaving current, like leaving polarity we will write. So if you apply the KVL in this fashion, so first we will get -5 plus minus, because currents always enters at the positive terminal and leaves at the negative terminal, minus. So now what will be the current in this element, because we are applying the in this loop, so I2 minus I1, because I2 is dominating, so I2 minus I1, so minus 10 into I2 minus I1, minus what is the current flowing in this element, 50 into I2. So this is the drop across this R2, so simply is equal to 0. I hope you are clear. See, simply you can write like this also. Supply, this we call it as the algebraic sum. This we call it as the, when supply voltage is equal to the drop across, sum of the drop across two elements. Just to like differentiate, I have taken these two types of equations. Okay, so even you can write it as -5 is equal to drop across these two. Like then we'll get 10 into I2 minus I1 plus 50 I2. If you send these two parts this right hand side, then you will get simply the same equation. Now we have the two equations and two unknowns. What are the unknowns? I1 and I2, and two equations. You just simplify this equation, find the I1. So simply we'll get I1 is equal to 0.3235 amperes. Now we'll do the same circuit by using the KCL. So already you know that the KCL is applied at the node. So this is the node point, we can say, where the R1, R2 and R3 are connected. So you just simply apply the KCL here. Okay, so as this at this point we don't know the voltage, so let us consider the voltage V, because we don't know, right, the voltage value here. So let us consider V. Now apply the KCL here. So what is the current coming into this node? So let us consider current coming is V minus 10 by 20, because the current is voltage by resistance, right? What is the voltage across this one? So we'll get V minus 10 voltage divided by 20. So what is the current flowing through this R3? So we'll get simply V divided by voltage divided by resistance, V by 10, plus, so what is the current flowing in this element? So V minus 5 divided by 50, so is equal to 0. So see, here we are considering that all the currents are flowing towards the node. We are assuming that, okay? So later you can change the direction if you get the negative value. Okay, so for our analysis we are considering, or we are assuming, all the currents are flowing into the node. So sum of the currents is equal to, there is no outgoing current, right? So we'll simply keep is equal to 0. So you have one equation. Now just simplify this equation. You have one equation and one unknown, so simply you will get voltage value, where V is equal to 60 divided by 70 volts. Now we know the voltage, this is voltage value. Now we want current I1, right? So this is the current I1, right? So the current flowing in the first loop. So what is the current here? We are considering V minus 10 by 20, right? So simply you just apply the voltage value here. What is 60 by 70? 60 by 17 minus 10 by 20. If you just simply solve this equation, you will get the I1. See, we got V value, right? What is the current here? V minus 10 by 20, right? This is the current. What is this current if you want? V by 10. What is this current if you want? V minus 5 by 50. So these three are the three currents. So now we want this current. So means we know already the V value. So you just simply apply this value here and get the V1. So I1. So I1 you will get 0.3235. Now in the both the cases you will get the I1 as same. So both the cases I1 as, whether it is by using KVL or KCL, will get the same value. So I hope you are clear with this KCL and KVL. Thank you for listening.